So there's an even simpler phenomenon at play here. Take a triangle ABC and a point Q that lies either in the interior of the medial triangle, which is actually shown here, okay, or in one of these three wedges that stick out of the triangle ABC, and they are extensions of the sides of the medial, okay? And we know that, and this is a well-known result, if Q is in one of these four regions, the Q-centered circumconic will be an ellipse. So I'm actually showing it right here. This brown ellipse is the Q-centered circumconic. Okay, it's a circumellipse. It passes through ABC, and if I move Q around, I'm going to change that object there. Here's a brown ellipse here. Now, as I move Q around, the area of the brown ellipse is varying. Okay, in the previous video, we actually saw the locus of Q such that the area was fixed and equal to that of the circumcircle. But that's not germane here. There's a very simple principle that I want to talk about. I'm going to take the barycentrics of Q and swap them. I'm going to permute them. So there's 5 permutations possible. And we know that the permutations, they're going to lie, so they are here. They're indicated as Q2, Q3, Q4, Q5, and Q6. We've seen many times that they lie on an ellipse which contains Q itself. So it's this ellipse over here. Okay? And we know that this ellipse is a dilation of the Steiner circumellipse of ABC, not shown over here. Okay, so what I realized was that if you actually draw the 5 circumellipses center on each one of these permuted positions of Q, so namely here on this picture Q2 through Q6, those 5 circumellipses, and they're shown here green, okay, they have the same area as the Q-centered circumellipse. So I would say this is the simplest way to word and the most generic principle, which is the barycentric permuting of the coordinates of the center of a circumellipse produce a new point, which if you take as the center of a new circumellipse or circumconic, is gonna, number one, make that new circumconic continue to be a circumellipse, and that circumellipse will have the same area as the original one. So you have 5 possible permutations, and they're all area preserving, and they preserve the circumconics as ellipses as well. They don't become hyperbolas or parabolas. So you can see this here, right? So if I place, I don't know, Q is over here, I'm permuting its barycentrics, you can see that all the new permuted barycentric points lie within the medial triangle. If Q is actually outside, you're going to see that the permuting will maintain magically all the 5 permutations within the outer wedges. So if I'm in one outer wedge, the permutation takes me to the other outer wedges. If I'm within, I stay within the medial. But the really cool result is that the 6 circumellipses will have the exact same area. And the reason I know that is because I'm showing the area of the brown circumellipse here, which is Q-centered, and here's the area of the other 5 circumellipses whose centers are the permuted locations of the Q point. Okay, guys, so I think this is a generic principle, and we saw specific manifestations of it in previous videos, but it suffices for us to prove that the barycentric permutation of the center of a circumellipse takes you to another circumellipse of the same area. All right.